All right. So this is the general relativity or the special relativity part of this, right? This is Galilean transforms, right? So this is just saying that what we think is going to happen, right? It turns out that there's problems with this, right? So for example, this guy's just saying we can just add velocities. If I'm on a car, right, and say we're watching this go by, right, and this thing is moving at some speed, say 30 miles per hour, right, and a pitcher throws a ball. I don't know why the picture looks like that, right? They throw a ball relative to them at 40 miles per hour, right? That we would see that ball going 30 plus 40. So in this case, we'd use a plus instead of that, right? And if they threw it the other way, we'd subtract or something like that, right? Um, and that the time is the same in both frames of reference, that objects cover distance when they're moving at a constant velocity at the same rate, right? Now, of course, the problem with this is that if you are in a frame of reference that's going really fast, right? So say we're standing here and let's say the person's going toward us. Let's keep it really simple, right? And let's say they're going at 0.6 the speed of light toward us, and they throw something at us at 0.7 relative to them, right? If we use the same maths that we use here, we would see that baseball coming at us at 1.3 times the speed of light, which is not possible, right? And so that's what this thing is for, okay? This guy here lets you add the velocities properly. Now, if you're adding these things, okay, you're going to put a little plus. So in this case, you would do the plus there, right? And you'd go 0.7c plus 0.6c over 1 plus 0.7c times 0.6c over c squared. Notice that the c's cancel in the denominator there, right? So really you can just go 1 plus 0.7 times 0.6, right? And what this will do is it'll give you the velocity that you would see that baseball, and it's going to be less than the speed of light, okay? But then, of course, the question is, what happens if we're going really fast, right? If we're going really fast, what happens if somebody shines a light at us, right? So let's say that they're going toward us at, say, the cart's going 0.6c, and we're there, and the person standing on here shines a flashlight at us, right? And a photon comes out of there, and it's going relative to that person 1 times the speed of light. Well, something really cool happens with this equation, right? So the speed, of course, we know that we're going to see that photon going the speed of light. It's going to be blue shifted because they're coming toward us, right? But something really cool happens with this equation, right? And that is that we get, well, let's just see what happens, right? So in this case, we're adding, right? So remember, if it makes sense to add the velocities, use a plus. If it makes sense to subtract, let's say they shot the light the other way or something like that, then use the minus sign, okay? But let's do this, right? So we've got 0.6c plus 1c all divided by 1 plus 0.6c times 1c squared, and then the c's go away, right? And we end up with 1.6 over 1.6 times the speed of light, which is just the speed of light. That's kind of cool, right? These equations are crazy that way. And you can go in here and like solve for one of these velocities inside there, and you get the same equation. These are crazy equations, right? Okay. And then this is the Lorentz factor. Okay, notice it's 1 over this minus this. As v approaches c, 1 minus this quotient here becomes 0, right? And then 1 divided by the square root of 0 becomes a big number, right? Okay. And so if we look at the Lorentz factor, and then we put the speed of light here, this is velocity this way, right? Here's the speed of light. The Lorentz factor doesn't do much for about 0.8, the speed of light, and then it goes up, and then it's an asymptote like that. Okay, it approaches infinity. Okay, so this is the equation you use These guys are equivalent. This is if you're going really fast, right? This is the passage of time is different, right? And in fact, that's what this guy is, right? A time interval in that moving frame of reference, time dilates, right? So the time that we see is the proper time, the time that they see in their frame of reference, right? Times this factor, right? So it's kind of divided by this guy, right? Right. So time. As somebody flies by you in a spaceship, you see their clock ticking faster. As they look out their spaceship, they see your clock ticking fast. Or sorry, did I say faster? Slower. You see their clock ticking slower, right? They look at your clock, and your clock is ticking slower. It's all relative. Okay, and then length will contract, right? Length will contract. And so as an object flies by, right, you end up with the length is the original length times the square root of 1 minus v squared over c squared, right? And so that, I mean, I'm just using this, I'm substituting this in for that, right? So lengths contract. Masses, by the way, dilate. So objects get more massive, and you can actually figure out how much energy they have by that amount that their mass has changed, right? E equals mc squared, right? So mass and energy are interchangeable. It's kind of cool, right? So objects, if you see a bus traveling by, right, a school bus, do they have 2 tires in the back? I think they only have 1, right? You have a school bus traveling by, and it's really 17 meters long, right? If it travels by you really fast, you'll see it as shorter, right? So here it's moving really fast. It could only appear to be 12 meters long, right? And then if you imagine that you had a tunnel that was 12 meters long, right? If the bus went fast enough, its length would shrink, right? And it would fit inside a tunnel that's 12 meters long. We would see it fitting inside this tunnel, which is kind of fun, right? As it goes by, we'd see this bus fitting exactly in the tunnel because it's going so fast that its length is shrunk to 12 meters, right? Okay. And the way we know it fits in the tunnel exactly is that we see the front begin to emerge at the exact time that the back enters the tunnel. Okay. Now the driver of the bus doesn't see that at all. They see the tunnel shrunken. The tunnel is actually shorter than 12 meters, and they see their bus as 17 meters long, of course, because that's how long it really is. That's its proper length, right? Okay. And so they see the front exit the tunnel way before the back end enters the tunnel, right? So events in our frame of reference that look like they're simultaneous because the bus is moving past us, right? Okay, are not simultaneous to the passengers of that bus. Okay. So that's that guy. So these guys are getting into space-time diagrams, right? And so if we do a space-time diagram, time, we go CT, I don't know, I think IB labels them differently or whatever, right? And then light, of course, is going to be a 45-degree angle, right? Because it's moving through space-time at the speed of light, right? And then, of course, real-world lines can be in this region here. So this guy, say you're moving at less speed than the speed of light, right? As is proper to do, right? This is our angle here, right? So this is our the velocity that we're traveling, right, over the speed of light, right? So the angle there between the time axis and our world line, the tangent of that angle is opposite over adjacent, right? So velocity over the speed of light. That's this guy. And I didn't, we didn't get into that. So this one's kind of fun too. This is the, remember that bus that looked like it's shorter, right? This is like the Pythagorean theorem in space-time, right? This is really cool. Check out Minute Physics. Search invariant, space-time invariant, right? Because, let's say you've got basically the concept is is this: is if you're looking at the shadow of something, right? Let's say it's 12 meters long, right? If you look at its shadow here on the x-axis, it looks like it's shorter than 12 meters, but there is a true length, right? So we have to do this axis and this axis. So here's the time axis, that's the x-axis, and we're saying that there's some invariant that has to do with this, and it's exactly the Pythagorean theorem. But anyway, there's great videos on Minute Physics. Khan Academy has great videos too about this. If you didn't get to it, I'm not going to try to talk about all that stuff. But anyway, I hope that helped at least a little bit. There we go.